Hello, my name is Mikhail Isaev. I'm a PhD student at Georgia Tech. Today, I would like to present you my research on ParaGraph, an application simulator interface and toolkit for hardware-software co-design. That work was partially performed while I was interning at Google and NVIDIA. I start my presentation with a short motivation that highlights a problem and looks at new opportunities. Then I will present my work on co-design infrastructure that exploits these opportunities to solve the outlined problem, followed by several case studies to highlight ParaGraph's versatility. Finally, I will say a couple words about my future work. So, let's get started. Consider hardware-software co-design for large-scale systems. Such systems are defined not only by hardware, but also by system-level software and applications they are running. Co-design crosses the domain boundaries that you can see on the scheme representing the system design cycle. A typical cycle includes the hardware design and deployment, system software tuning for the new hardware, followed by application tuning and more software optimizations. At this point, we usually know current hardware limitations and go back to the whiteboard to design next-generation hardware. However, co-design studies often don't cross all the boundaries. They usually optimize software for existing hardware or design new hardware using simplistic application models. And searching for possible reasons, we argue that what's at fault is the lack of the infrastructure representing an application, future hardware, and necessary levels of system software tailored specifically for the design system. In our view, co-design lies in the intersection of application, hardware, and software. The tool for co-design should effectively model all three of these components. Let's take a look at the co-design landscape now. One of the new applications influential enough to define modern systems is deep learning. Deep learning already helps both companies and research institutions to solve their tasks. It has a growing appetite for computational performance with which system designers struggle to cope. That drives improvements both on the hardware and software sides of the system. On the hardware side, deep learning has already pushed computer architecture into the age of new renaissance. Many large companies that work in the area of artificial intelligence propose new accelerators, while other companies utilize graphical processing units, or GPUs. In both cases, hardware is more specialized than typical central processing units, or CPUs. But at the same time, it's much simpler to learn how it operates. New hardware requires new software, like compilers, low-level libraries, and high-level frameworks. They look dauntingly complex, but hardware simplifies these software layers as well. The image shows a compiled representation of a simple neural network. On the one hand, it looks very complex for something like a manual analysis. On the other hand, every block represents a multi-instruction operation or a kernel call. The level of detail is much coarser grained than what you typically get from a CPU compiler, such as LLVM. So that's the stage. Now let's talk about ParaGraph. We propose ParaGraph, a tool for large-scale system co-design that mimics actual software hardware stack and implements previously missing pieces shown in yellow. We designed it to interface network simulators and complex application models considering all the previous limitations. Such interface effectively decouples application modeling, a job that hardware simulators are not good at, from hardware modeling. That makes the life of network researchers much simpler. Providing an API also helps application performance engineers to use detailed network models of future hardware to design the libraries before the systems get deployed. It makes co-design a really bidirectional process. We can subjectively compare ParaGraph to other modeling approaches, keeping in mind that ParaGraph is not a simulator, but rather a tool to interface together different pieces of modeling infrastructure. Compared to detailed RTL or cycle-accurate models, ParaGraph provides better scalability, ease of use, and network support. Compared to FPGA architectural models, ParaGraph is much simpler to use, with scalability not limited by the size of available FPGAs. Compared to network simulators, ParaGraph provides much better application and node fidelity. Compared to pure analytical performance models, ParaGraph has better network and application fidelity. Even though ParaGraph is not necessarily the best in every category, it doesn't fall short anywhere and behaves as a balanced approach. ParaGraph is built around existing infrastructure. It connects the compilers on the front end with hardware simulators on the back end. To model computational node architecture, ParaGraph uses refined models, such as available in optimizing compilers. Compilers can provide detailed application models from high-level frameworks like TensorFlow or JAX to ParaGraph IR. We use an internal translation mechanism to transform instructions that hardware simulators don't understand. The runtime provides available instructions to simulators via its instruction queue. ParaGraph IR consists of very simple building blocks. They are general-purpose instructions like delays, control flow instructions like loops and conditionals, and various types of communications. Mind that these instructions are macro instructions, such as matrix multiplication or AllReduce collective. As such, granularity of IR is much coarser compared to, for example, LLVM. ParaGraph works with a single program, multiple data, or SPMD applications, represented as a hierarchical graph where the nodes are instructions, while the edges are control and data dependencies. You can see such a graph on the scheme. Here you have a while loop instruction with two subroutines, loop body and loop condition check. Inside the loop body are some computation and communication instructions for gradient updates. Instructions in this context are coarse-grained macro instructions like kernel calls. Each instruction is composable and may consist of subroutines filled with other instructions. Finally, the application graph is not statically scheduled but dynamically executed. We can see how ParaGraph executes the graph from the previous slide on the scheme. ParaGraph scheduler recursively executes instructions following the hierarchy. It starts with the resolving instructions dependencies, and then it begins executing an instruction and checks if it has any subroutines. The hierarchical structure implements control flow similar to XLA HLO IR. The hierarchical structure also supports the translation mechanism, which we will describe in several minutes. In the end, the simulator gets a partial trace dynamically generated by ParaGraph. The final instruction execution order depends on how the simulator executes and completes each instruction. That differs ParaGraph from a trace-driven simulator, where you are perpetually stuck with the instruction order generated by your existing hardware to model your future hardware that may work very differently. This animation with a toy graph demonstrates how dynamic graph execution works. In the beginning, the simulator can fetch all the instructions without dependencies, and in this graph it is only instruction A. After instruction A finishes, it unblocks instructions B and C depending on its result. The simulator executes instruction B and C concurrently. Depending on what instruction executes first, we can get a different execution order. For example, if C finished first, we could fetch instruction E for execution right away. Let's imagine that B finishes first. Then nothing happens right after that. Instruction D that depends on B cannot start execution because it also depends on C. When instruction C finishes, instructions D and E can start immediately, as they have no pending dependency and nothing blocks them from the beginning of execution. After that, ParaGraph only waits when instructions D and E will finish. After all instructions return from the simulator, ParaGraph ends the application graph execution and the simulator halts modeling. Another important part of ParaGraph is the translation mechanism. What if we don't have collective implemented in the interface simulator? We can use the hierarchical graph structure to build complex communication algorithms inside collective instructions. These algorithms can be composed of simpler algorithms or similar to how we do it in software, actually. It only takes a couple hundred lines of code to implement a typical translation that uses previously available simple building blocks. We can start with a single AllReduce instruction with some computation inside that will correspond to a reduction part. We can expand AllReduce as a sequence of reduce scatter and all gather. Reduce scatter also implements a reduction copying it from the original AllReduce. If you want to implement an algorithm for particular topology, for example, a unidirectional ring, these instructions expand into a chain of send-receive exchanges. Reduction in reduce scatter implementation will be scaled down to represent a partial reduction status after every send-receive step. Similarly, ParaGraph helps build even more complex algorithms like optimized 2D torus algorithms we will talk about later. All that application complexity is hidden from the simulator under a thin API of the ParaGraph runtime. A simulator that wants to support ParaGraph opens a graph stored in a protobuf, and creates a scheduler for it in the network terminal model of the simulator. The simulator reads instructions from the scheduler queue using getReadyInstructions call and puts the corresponding event in its event queue. When the simulator starts modeling the event, it calls the instruction started function, and when the event is over, the simulator calls the instruction executed function, providing mode time to both. ParaGraph does the instruction-related bookkeeping, and at the end of the execution, it logs a runtime trace with execution timestamps for each of the instructions. This scheme illustrates how ParaGraph can build a modeling workflow for a deep learning application. We can pick a neural network training script written in TensorFlow or JAX and compile it with the XLA compiler. ParaGraph uses compiled representation to translate it to its graph format using the HLO bridge. During bridging, we can crawl the graph, separate computation and communication instructions, and utilize the roofline model to annotate computation instructions with their projected execution delays. After that, we obtain composite graph that represents a distributed SPMD application. We can translate them into individualized graphs corresponding to each modeled network terminal. They only have information about the instructions executed by the corresponding network terminal or related to them. Then these individualized graphs are provided to the simulator. Now that we are familiar with ParaGraph architecture, we can see what kinds of studies and co-design workflows it can support. The goal of first study is to find an optimal AllReduce algorithm for a deep learning accelerator. Typically, collective algorithm performance depends on the communication size, as some algorithms are best for either network latency or bandwidth, but typically not both. This study also wants to verify that our hardware design doesn't bottleneck our optimal algorithm. If we find out it does, we would like to alternate it before it's too late. We also want to check whether system size affects the algorithm's optimality. Consider a system with 32 accelerator cores. We can organize them as a 4x4 system of dual-core chips or an 8x4 system of single-core chips. We can also provide a different amount of local bandwidth between the cores. Even with a simple ring, AllReduce algorithms result into a two-dimensional lattice. We can see on the left chart that dual-core design provides better latency compared to a single-core one. We can also see that providing 2x local link bandwidth is necessary to match internal bandwidth with off-chip bandwidth and achieve about 2x performance improvement. Similarly, it gets more important in the case of an algorithm optimized for a 2D torus. We need to provide 4x local bandwidth to explore the algorithm concurrency in 2 torus dimensions, both of which are bidirectional ring. We can pick the best combination of the 4x4 dual-core system with 4x local bandwidth for the optimal algorithm search between bidirectional ring, mesh, and torus algorithms. We can reduce the data between the cores in torus and mesh in various ways. First, we can use a separate local exchange step, or SLE, between cores reduction. In this case, we effectively have 3 smaller reduction rings. Second, we can add cores on the last reduction dimension and implement integrated local exchange step. In that case, we have 2 larger reduction rings. We see that the optimal algorithm should combine several base algorithms. However, the scheme doesn't provide a clear view of what algorithms are candidates for a pick. Looking carefully at latency distribution, we can conclude that although mesh-based algorithms provide lower average execution time, they have higher variability. It means that some processors in the system finish reduction faster than the others. As the slowest component usually determines the network performance, we have to pick a torus-based algorithm due to its better stability. Among SLE and ILE options, we see that the first better is for small message performance, while the second is better for the large ones. However, it isn't clear what the large message or small message means. After running experiments on 3 various system sizes, we can conclude that this is indeed not a trivial question. The inflection point that corresponds to the message size when one algorithm bests the other depends on the system size. However, ParaGraph allows us to answer it even during the future system modeling. That result differs from a typical analytical model output, where communication time usually doesn't directly depend on the system size. So what did we learn during this case study? First, we can co-design software and hardware simultaneously, as we did with accelerator microarchitecture tuned together with the AllReduce algorithm. Second, we can start optimizing communication libraries for future systems before deployment. And third, ParaGraph demonstrates scalability up to 512 nodes in our studies. The goal of the second modeling study is to verify ParaGraph's fidelity against application trace obtained from the actual hardware run. We built a new workflow connecting the production-grade ML compiler with the network simulator. We aim to verify the fidelity and applicability of using ParaGraph with analytical modeling and discrete event simulation for system performance matching. This workflow helps to optimize systems for a particular set of production applications that not only verifies ParaGraph as an accurate tool, but also allows to quickly run various what-if studies, picking the best ideas for future system iteration and optimized performance for a very specific set of important applications. On the top plot, we compare ParaGraph with the roofline core model as a blue bar against the application trace, green bar, obtained on the TPU V3 system consisting of 32 chips with 64 cores total. The average difference between the two is around 25%, but it reaches 70% in some cases. That is due to the optimistic nature of the roofline model. It assumes that the accelerator runs all the instructions with 100% efficiency. The difference between the roofline and the trace highlights the inefficiency of the hardware running a particular application. The accuracy dramatically improves if we use ParaGraph with information about memory accesses and computation instructions from the trace, as in red bar. We can see on the bottom plot that the network performance projection obtained with a detailed simulator provides a modeling error of around 5%. We can even assume what the AllReduce algorithm profiled system uses. We also can run a performance projection for different system sizes using the same application trace. In this case, from the same profiled ML workload trace, we project the performance of system with various scales. We can change topology, link bandwidth, or other network parameters to obtain performance projection for a slightly alternated system. So what did we learn during this study? First, the node model that ParaGraph employs is not optimal. However, it's not a limitation of ParaGraph, just an artifact of the roofline model. We can interface ParaGraph with a better tool to model node or use a model from the vendor if such is available. Second, even with a simple roofline model for a node and a high-fidelity network model, ParaGraph can make accurate network performance predictions. The roofline model shortens execution time and stresses the network even more, but it doesn't make the network part of modeling less valid. If you have a system similar to the one that we want to model and that we can profile, the accuracy can improve dramatically. Third, we show the flexibility ParaGraph provides to create different modeling workflows based on the needs of particular user. In the third case study, we model a future system that uses switches with in-network reduction implementation. Such devices are only available in a simulator, not in real hardware. We build a different modeling workflow that interfaces JAX applications running on GPUs with a proprietary network simulator developed at NVIDIA. This simulator implements AllReduce for both in-network and in-processor reductions, so ParaGraph doesn't utilize its translation mechanism. We know that in-network reductions implementation can provide up to 2x network throughput, but we want to establish any significant performance gain for real applications. We are also interested to see if we can optimize network topology to cut network cost. As we saw previously, AllReduce, a dominant deep learning communication pattern, can depend only on neighboring traffic, opening up some opportunities for cost cutting. First, we need to formally verify that the network reduction achieved performance improvements on synthetic traffic. We ran the study for several factory configurations with different top-rank factors represented by different colors on the chart. We can tell that lines corresponding to in-network reduction support, solid line for each color, provide about double network throughput gain over a processor reduction, dashed dotted line. However, networks with various top-rank factors perform differently. It indicates that AllReduce traffic is modeled as all-to-all and not neighbor exchange. It is typical for memory semantic networks like the NVLink-based network of GPUs, so the study suggests possible protocol improvements. Next, we assess the performance of several real neural networks. ResNet-50 is a data parallel convolutional neural network with a small model and communication size. A transformer is a data parallel language model with a large model and communication size, and Megatron is a model very similar to the transformer, but it utilizes both data and model parallelism. Here we see somewhat unexpected results. For data parallel applications, in-network reductions don't make much difference in performance. That probably happens because communication and computation can efficiently overlap, which ParaGraph accurately models. At the same time, network tapering affects the performance of data parallel application more significantly. That indicates that AllReduce demonstrates all-to-all traffic in the simulator and is similar to our synthetic traffic analysis. Model parallel Megatron shows a completely different pattern. Its communication is rather significant and cannot be overlapped. In-network reductions provide a sizable boost in performance. At the same time, tapering the network doesn't impose a performance penalty. That's probably because by utilizing both model and data parallelism, we actually reduce the communication volume of all-to-all. So what did we learn during this study? First, ParaGraph can provide traffic from various applications to various simulators. Second, we can see that ParaGraph can provide information to the hardware modeling level about current software optimizations, for example, communication with computation overlap. Third, this study demonstrates that the importance of assessing improvements in hardware on the real applications, as hardware optimizing might not show measurable performance improvements while being expensive to implement. We also see that performance optimization should be delivered not just on hardware but across the stack, like wider adoption of model parallelism. Finally, ParaGraph reveals several weird corner cases in the current hardware model and suggests some optimizations. Finally, let's jump to a conclusion. I presented ParaGraph, a novel co-design tool for large-scale application systems. ParaGraph provides real software models for hardware people and future hardware models for software people. It caters to different engineers and researchers in application, system-level software, networks, and large-scale systems areas. It is open-sourced and available on GitHub. In the future, we would like to provide support for more tools on both the front end and the back end. Specifically, we'll be looking at SST integration and supporting newer software infrastructure such as CUDA graphs. On the algorithmic level, we could extend translation capabilities to cover popular HPC libraries that implement generalized matrix multiplication or fast Fourier transform kernels. Finally, we see that ParaGraph can be used not only for performance prediction, but also efficiency and cost, helping to optimize the systems with respect to performance per watt or performance per total cost of ownership metrics. So thank you for your interest in my presentation and our tool.